Okay, good. We're back to data analysis. I did make a Google Doc. It is at this short URL. All capital TASI. dwh.gg, TASI. If you go there, you should get to a Google Doc where you can type in subjects. Oh, sorry to people all the way on this side of the room. That was dwh.gg/capital T, capital A, capital S, capital I. If you go to that link, you should see a Google Doc where you can brainstorm topics. And if you see a topic there you're interested in, put pluses after it. Some people in the break pointed out that I was probably invited here because I know how to do statistics in large-scale structure projects. And I've been talking very generically about data analysis. So if you want specific large-scale structure content, make sure you say so there, because we could build future examples around that. The example I'm going to do right now is so trivial, it's not going to have anything to do with large-scale structure, except indirectly in that it involves likelihoods. Good. Did anybody confirm that that link works? It works. Boom. Thank you. Okay, good. Good. So we'll crowdsource it. We'll see what I'm doing on Wednesday. Tuesday, I will talk about MCMC. That is tomorrow. I'll talk about MCMC, but then Wednesday we'll be into crowdsourced territory. Oh, and one thing I should say, I reserve the right to assemble lectures out of the topics. And I won't talk about subjects that I know nothing about. Although that doesn't always stop me. Okay, good. Let's do a very, very simple example problem. We're going to set up a very simple example problem. We're going to write down assumptions. We're going to show how those assumptions feed into making a likelihood function. We're going to then see how those assumptions drive us to one and only one, well, really two and only two ways of kind of doing inference in the problem. And then we'll talk about how we would analyze whether our assumptions are okay in the problem. And then we will ask, like, what kinds of things happen if you change the assumptions? How does the model change? So I'm going to start on the center board because we'll get our basic assumptions here. So here's my data. There's some parameter space, x, y. At locations in x, I'm going to measure y. That's called physics. Let's make the things have different size error bars. Okay, good. At a set of positions x, I've measured y. So if this data point is point n, if that's data point n, then it is at xn, and it is at yn, and has some uncertainty on it, which you might call sigma n, which is like this 1 sigma, say, uncertainty, which are sometimes called error bars, but they should be called uncertainty bars, because if they were errors, we'd fix them. Yes? Oh, am I assuming? We're about to get on to what we're assuming. That is one of the things we're going to have to assume to write down a simple model. If we don't forget that, because we're going to unassume that later and show that this problem becomes a lot harder if you let there be uncertainties in both x and y. Which is remarkable because that doesn't sound like a big change, and yet it's a huge change structurally to this problem. Yes? Good question. That will also fall into the category of our assumptions. So we're going to write down a set of assumptions for this problem so that we can do some data analysis. Right now, if you're just presented with these data, if you were presented with these data and asked to do data analysis, you'd be like, what? Like what? You have to make assumptions to even move. We can't do anything right now just looking at that. Like, I guess I could make this plot. That's about all I could do without further assumptions. Yes?
So visually, as if your uncertainty bars do not look symmetric, but you have only one symmetry.
Yes, I think I was intending them to look more or less symmetric. I'm apologizing for that. But that's another, don't forget that, because that's another thing we should consider when we break our assumptions. Because we're going to make some very simplifying assumptions. And when we make those assumptions, the nice thing is we'll make a set of assumptions that will drive us to a very unique data analysis solution in this problem that we kind of have to do. But one of the things that's a little disturbing is it's a lot of assumptions. And that gets back to that kind of subjectivity. We're going to have to make a lot of assumptions in order to get a well-defined procedure to perform here. And then we'll find as we break those assumptions, it will greatly complexify our procedure. Okay, good. So assumptions have already come up. One assumption that's come up is uncertainties only in X. Oops, Y. Meaning X values are, that doesn't mean that your X values are known perfectly. There's nothing in the world you can know perfectly. We can only measure times to something like 10 to the minus 11 seconds, so we don't know them perfectly. And we only know right ascensions and declinations on the sky to 11 digits of accuracy, so we don't know them perfectly. But the point is the uncertainties in X are ignorable. The assumption is really that the uncertainties in X are ignorable or will not affect our results. Okay, anybody have some suggestions of other simplifying assumptions we tend to make when we're faced with data like this? Yeah. What he said. Gaussian noise. Good. Meaning, and we don't really know what we mean yet. We're about to make it very specific. It's a little not confusing, like what does this mean, Gaussian noise? Like, presumably these Y values are the values that were read out by some device. So what does it even mean for there to be noise? You know, like if I counted the number of people in this room, well, in what sense would there be noise? So even the fact that we've used the word noise here means we're somehow have some feeling that the data are generated by a noisy process. And there's some deeper assumption which we're not even going to be able to write down because it's so deep we can't even see it. Yes? Symmetric uncertainties. Good. Gaussian implies symmetric, but another way to say it would be, let's call it, say again. That the error bars are symmetric, which is another, but if we've assumed Gaussian, it means that the mean of the Gaussian is at the data point. So you could say like zero mean. Meaning the deviation between what was measured and the true value of Y is, and somehow we have an unbiased estimate for Yn for each object. Yes? Good. We need to decide something about data point correlations, and the simplest assumption, although this is an assumption that's easy to change. We're going to make a hard assumption here, but there's actually this is actually not a strong assumption in the sense that the method we write down will actually be very robust to changing this, which is uncorrelated. Well, let's not write it that way. Uncorrelated is a very bad thing to write. Independent data.
The uncertainty bar is also being independent?
One interesting question is whether the uncertainty bars are themselves data.
You did say that area there was your data.
So. Good. So excellent. So the question is, are the uncertainty bars themselves data? And that is actually, that is now, that falls squarely into the category of assumption. So remember, we're going to try to write down some kind of generative process for our data. And we have to decide what part of our data are we going to generate. Are we going to generate the y values, or are we going to generate the y values and their uncertainties, or are we going to generate the y values, their uncertainties, and the x values? See, there are different models at different scales where you might treat these sigmas as known, like maybe maybe this is a thermal noise, and you can measure the temperature in the system when you took the observation. So in CMB experiments, when people are imaging the cosmic microwave background, they're using generally thermal detectors with a thermal noise, and so they can compute these values very precisely from a kind of instrument model perspective. There are other times where you don't know much about this at all, and these themselves become model parameters, and then you have to generate them as well. Yes?
So when you first wrote that, I thought that was applying to the data set as a whole, not to each individual point's error uncertainties. So like, do you have to assume both if you assume one?
Strictly, the noise on any one data point can only be Gaussian once you know the uncertainty. So conditioned on knowing the uncertainty, you can assume that the noise is Gaussian. But if you don't know the uncertainty, then you really can't assume that the noise on any data point is Gaussian. So,
The overall set, does that have to have also? So like if you're getting
good. Good. There might also be some, in addition, there might be both a measurement noise and some kind of sample variance as well. Good. We haven't even got there yet, but that is a very good question. Notice that these are questions about each individual data point. But we're going to start to have to make assumptions about the data as a whole, like how the data as a whole are generated. So hold that thought for a second, because I just want to finish this error bar, or this uncertainty estimate thing. The simplest assumption we can possibly make about the uncertainties, like literally the simplest, and we often make this because it makes methods easy, is to assume that the sigma n values are known and correct. And that sounds like a strong assumption, and it is. One thing to point out is in no experiment that has ever been done in the history of mankind have we ever known our uncertainties. And there's a very deep reason you can never know your uncertainties. And that is, how would you empirically verify that you know your uncertainties? The answer is you'd have to take so much data that you can look at the uncertainty on the uncertainty. And since the uncertainty is already a second order statistic of your data, the uncertainty on the uncertainty is like a fourth order statistic on your data. And even the LHC doesn't have enough data to measure confidently fourth order moments of its general error properties. So there's always some magic in your noise estimate. Now, some people would say, a lot of astronomers say, but we're counting photons. So we know that we have Poisson noise, and once you've counted thousands of photons, it's very close to Gaussian, and you really know that it's the square root of n is the variance, or the root variance. And that is, there's an element of truth there, but that assumes that nothing else entered into the telescope readouts other than the photon noise. There was no noise in the A to D converters, no noise, no thermal noise, no dark current, no zero, nothing else was contributing to the data, and that's simply wrong, first of all. And second of all, even if it wasn't wrong, how could you verify that it wasn't wrong? You'd have to take an unimaginable amount of data to verify. So this assumption is very wrong. We make it all the time. We have to make it to make various methods tractable, but it's not a good assumption. And we'll come back to how we would test that. We can test it, but we can't test it very precisely. One thing is that almost all methods where you infer the uncertainties are computationally challenging. We do some problems like that, but they're very challenging. Well, I'll come back to that when we modify. Yeah? Good. good. The comment was, so I haven't been repeating all the comments and questions. I'll try to get back onto that. The comment was, can't we just sort of overestimate our uncertainties and then we'll be conservative? So yes, in some sense, yes, but there's another equally true sense in which the answer is no, because if we imagine that there's a sample variance and we try to infer the sample variance as well as other properties of the population, it turns out our estimate of the sample variance is very sensitive to what we believe about these uncertainties. And as you raise them, the inferred sample variance goes down, and as you lower them, the inferred sample variance goes up. And so, in fact, there's no truly conservative choice. And it's a sad and terrifying thing that this, the dumbest of all problems, is already intractable, impossible, and complex. Okay, good. Those are some nice assumptions about each individual data point. Now let's make some assumptions about the population of data points. What's something simple we could assume about the population? A linear model, and y is a function of x. Those are two very simple things we could assume. That y is just some function of x, and we're trying to infer that function. So this function is going to have some parameters theta and 5. Y is a function of x. Good. And we're going to we might even make it a linear function of x. That would be a nice thing to do to make our lives very easy. Or we could make it a linear combination of functions of x. The word linear is kind of overloaded, unfortunately. Linear can mean linear in these parameters or linear in these values. It turns out linear in these parameters is more important for data analysis purposes than linear in these x's. So if I made this to be like a sum of sines and cosines of x, that would still be linear. That still could be made linear in these parameters, but it would be nonlinear in the positions. So, but anyway, let's hold that thought for just a second. We'll come back to exactly how restrictive we're going to make this function in a minute. We're not done. There's the sample variance issue, which is it the case that each y value is just this line plus an uncertainty, plus a noise? Or is this y value this line plus an intrinsic scatter plus the noise? See what I'm saying? Like, is there also some sample variance? And I will say no intrinsic scatter because it's still the easiest thing to assume. I'm trying to do this easiest in every case. And let me just write this. Y is a function of x. Y equals f of x and then semicolon theta. And by the semicolon, I just mean this is a function of x parameterized by some additional parameters. Everybody with me? Yeah. First of all, the question is, this might be pedantic, but does 5 also include 6? The first part of my answer is, the point of this lecture is extreme pedantry. And you will be rewarded the more pedantic you become, the more rewarded you will be. Because one of the points of this is to really draw out all the little things. Second of all, it depends exactly what you mean. I mean, it's a little ambiguous here. These are all written in human language. We should obviously write each of these things in pseudocode. Right? Because it's really, we would want to write, in some sense, there's different ways to think about these assumptions. One way to think about these assumptions is it is parts of a computer program that would generate data like this. See? Because if you can write a computer program that will generate these data, then in principle you can do inference. See? Like, because the computer program becomes your model of the world. And we can do inference in that model. By the way, the word model is also overloaded. And I'm going to take a very particular view of the word model. I will tell you when we have a model. We're close, because this set of assumptions is close to complete. I mean, there's additional assumptions like things about the topology of X and stuff, which we're not going to think about. There's some really deep assumptions, which I was kind of getting at earlier. Okay. So now, if I put all these assumptions together, then I can start to write down kind of probabilistic statements about data points. So for instance, I could write something that looks like I could encapsulate a lot of these things by saying that the probability, there's kind of a probability distribution for what I would expect for the nth data point. Like not looking at the data, just looking at these assumptions. What do I believe I'm going to get for the nth data point? Well, it could have a wide range of values, the nth data point, but I expect that nth data point, or my probability for this nth data point depends only really on the x value of the nth data point, because I need to be able to evaluate f of x. It's going to depend on theta, the parameters of my function, and it's going to depend on my belief about the uncertainty on the nth data point. And since we've assumed that the data are independent, it doesn't depend on any other data points, which is a little convenient in terms of writing things down. And because the uncertainties are only in y, I can kind of condition this probability on x. I don't have to think about generating x. I know the x's somehow. And I don't have to generate the sigmas because I said they're known and correct. So I don't have to generate them either. So I only have to generate the y's, and everything else is, well, these two things are known. This is something we're going to have to infer. The theta is something we're going to try to infer. Okay, good. And this probability distribution is going to be Gaussian. I will always use n for a Gaussian, although I think this is probably the only lecture in which I'll ever mention a Gaussian. But anyway, is a Gaussian for yn with mean f of xn given theta. That's the mean of the Gaussian. And the variance of the Gaussian is sigma n squared. So this is the mean. And this is the variance. And this I would call a generative model. This, for me, is very close to a model. We need only a couple more things, and we have a model. But this is the model. Notice that it's the only model I could write down. It's the only likelihood, or it's the only probability distribution I could write down given those assumptions. I got nothing else. I haven't told you how the thetas are distributed. So I didn't say anything about how the thetas are distributed, so I can't say anything stronger about theta. And I assume that these things are known. So this is about all I can write down. But it turns out this is enough to do a lot. We can now do a lot in this problem. Good? There's something else I was going to say.
Is there a difference between the variation, so if your uncertainty bars on each individual data point
Yeah.
is not the same as the distance from that point to that line? So there's, if you would go
Yeah.
with the displacement from
Yeah.
your central function, if we were to take that as your uncertainty, that would be a different value of sigma n.
That's right. So one thing I think we'll find when we do this inference, we're going to find that some of these assumptions are questionable, I think is what's going to happen. That's my expectation.
Formally, sigma n is the uncertainty bar, not the displacement from the central line.
Exactly. Sigma n is the experimenter provided us with those metadata. You can think of these things as being housekeeping data. This is your data, and this is like metadata that the investigator tells you. The investigator tells you at time 13.615.665.992, we took a measurement with this uncertainty, and we got that. So that's one way to think about it. These are like metadata about this observation. Good. I think as we go, we're going to find that this model isn't so great, given those data. Luckily, I didn't specify those data, so. Okay, good. One thing I was going to say is, this is a complete aside. Don't write this down. Imagine I made the model. This is totally, I've got to write this like, I got to write it like on a sideboard. Imagine I made the model y of x given theta is a cosine kx plus phi. So my parameters are a, k, and phi. Those are my three parameters. So I could write theta as the vector a, k, phi. Okay? So this is a possible model that I could have written down for that problem. This has three free parameters, right? Do you see that there's a setting of a, k, and phi that exactly pierces the center of every one of my data points?
Very high frequency one.
An extremely high frequency, right? Can you see that there would be such a thing? And then once you see that, you see how I could add another data point and there still would be a solution? Which means before I added that data point, there was an infinite number of such solutions. Such a dense infinity that I can add another point anywhere and still find an infinite number of solutions for the next data point I put in. Do you see how that's possible? Do you see how that's a weird kind of paradox? Because this has three free parameters, and that's some, I don't know, 12 data points. 13 data points. You see that? Do people get that weird paradox thing? I think one of your homework assignments will be to resolve that paradox. Good. We're not going to talk about that model. That model is too frightening. By the way, one of the interesting things about this model is not linear in the parameters. Remember, there's these two words, linear has two different meanings in this context. This problem is not linear in the parameters because these two parameters appear inside a nonlinear function. So it's a nonlinear function of the parameters. And once you get a nonlinear function of the parameters, a lot of the ground you're used to standing on gets a little shaky. Okay, good. So I think we should make an additional assumption, which is that the model is linear in the parameters so that we can push aside those kinds of issues till later. So I'm going to make the seventh assumption, f of x given theta is linear in theta. Okay, that's going to be a seventh assumption, which I'm adding to really make life easy.
That seems like a really restrictive assumption.
Unbelievably restrictive, yep.
You can't even fit an exponential.
No, you can if it's exponential in x.
But if you I looked at exponential with an arbitrary constant of decay.
That's right, you cannot, exactly, yes. Right, this is a ridiculously restrictive assumption. This assumption is outrageously restrictive. We make it a lot. And one of the reasons we make it a lot is that it makes life a lot easier. For instance, under these assumptions, we're going to have a convex problem. This problem will be convex under these assumptions, meaning we will be able to just go downhill from any first guess and get to the right answer once we decide what that right answer is. Yeah. Yeah. Good. Great. So it's still the case that we have the property. So also in answer to your question, any function can be written as a sum of basis functions. So we could do a basis transformation and then work in that basis. And indeed, you've made a recommendation. We could add in 2000th order polynomial here with 2001 coefficients, and then we could fit anything, certainly 13 data points, no problem. But notice that in that case, you clearly have the situation where if you want the freedom, you have to add the parameters, which somehow is going to help us. That's what helps us. That's what saves us in this problem. But good. Hold that thought. Hold that thought because it will come back. Good. Now, I'm now going to rewrite this. I'm going to vectorize now. So I'm going to vectorize this problem. So I'm going to deal with all the data points at once because I want to write this in a certain way. But I can just remind you, just a little reminder, the Gaussian for a Gaussian for some vector y given some mean, let's call it mu, and some variance v. Now notice, so say this is a d vector. Then this is also a d vector. And this v becomes a d by d tensor. And it is truly a tensor in the geometric sense. Remember geometry? Tensors and matrices aren't necessarily the same thing. Matrices are representations of tensors. This is actually a tensor. And if that means nothing to you, just erase that from the record. But geometrically, this thing is truly a tensor. And a variance, this is a variance. It's a 2-point statistic of the data. This is a 1-point statistic. It's a mean. So the mean is a vector like the data, and the variance is a 2-point statistic, so it becomes a tensor. And you can thank God we're not dealing with skewness, because the object's horrendous that comes next. But now that this thing is 1 over 2 pi v to the 1/2 exp. So first of all, these things mean determinant, and I mean determinant of 2 pi times the tensor, not the determinant. Sometimes people put in a 2 pi to the d over 2, which is a strange thing to do because anyway, 2 pi times the tensor to the half, take the determinant of it to the half power, and then there's an exp of negative, and now we go, oops, I need a negative 1/2, negative 1/2, y minus mu transpose v inverse, and now you guys are not going to be able to see the end of the expression. Sorry. Y minus mu. This is y minus mu transpose. This is y minus mu. They're dot producted into a v inverse. Is that, people seen that before? Good. That's just the statement of the d-dimensional variance, or Gaussian. I just wanted to write it down carefully. This thing has some beautiful properties. One beautiful property is that this is just notice this is a separation between 2 points in D space, quadratic form with a non-trivial metric tensor. That's where I said it's geometry. Geometry, relativity, all those things. This tensor is Hermitian, like the metric. Well, the metric is symmetric, whatever, it's symmetric or Hermitian or whatever. This is truly a symmetric tensor. It's a tensor. Tensors have to be symmetric. Notice also that if you fully evaluate this thing, which you don't always have to do, you need to take a determinant. That is very bad. Evaluating determinants is like doing integrals. And you might think a determinant, well, it's just some operation on the contents of the vector, the matrix, blah, blah, blah. But computing a determinant is very similar to doing an integral. Why is it very similar to doing an integral? Because inverse the determinant is the prefactor that ensures this thing integrates to unity. So this is the integral of that. If you integrate that over all of space, you get that. So the determinants are like integrals. And so if you have a 10,000 dimensional space, you have a 10,000 by 10,000 matrix, computing its determinant is like doing a 10,000 dimensional integral. And that's why very few people can compute determinants accurately. There's very few accurate determinant codes in the world. Yes?
It depends only on the linear transformations of the vectors, right? B is not a function of position.
Under these assumptions, it's not a function of position. But if we modified exactly one of these assumptions, it would become a function of position.
In that case, the difference would be infinitesimal.
What difference?
Like a dx. The y minus mu should be like a dx. X and y are not dense.
Oh, I see. Yeah. No, you'd have to do integrals. One of the reasons we made these assumptions is so that we don't have to do horrendous integrals. Yeah, exactly. Yeah. And those integrals become impossible quickly. And that's why we're going to switch to MCMC next lecture, because MCMC is a way of doing those integrals that we can't afford to do through continuous methods. Yeah?
I think our previous assumption that each data point is individual Gaussian. But for this form, it seems you mix of each point. Right? This point between the other point.
Good. So this is a much more general expression than what we need. Yes, absolutely.
That one just assuming B is diagonal.
Good. So the comment is that this expression looks like it's going to deal with all of our data points simultaneously, and it is. And we don't need to because they're all independent, or they're all independently drawn. That's true. So that means that's going to put some structure on this variance tensor, which, as you identify, is going to be diagonal. Good. So let's translate this into this form. We do need to think about one more thing, which is that this is the probability of a single data point. The probability of all D data points would be the product of these probabilities, because probabilities multiply. And if you notice, when you product these Gaussians, you're kind of adding up things in the exponent. And this is where you might remember chi-squared. You've done chi-squared means something to people in the room? Okay, good. By the way, this is a huge point of confusion when physicists talk to statisticians. For physicists, chi-squared is a statistic. It's data minus model squared divided by error squared, right? For a statistician, chi-squared is a distribution that has certain kinds of properties. And you can spend a whole afternoon with a statistician, and at the end they go, oh, and you realize your whole conversation was wasted. So that's one of those many stumbling points for. So if I write this out, so now I'm going to translate this into this form, which is trivial. I told you the model would be trivial. I promised you that. I'm going to make these definitions. Y, the vector y, is going to be the column vector of y1, y2, y3, ... down to yd. Right? And the variance, mu is going to be f of x1 given theta, f of x2 given theta, dot, 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 down to d. And v, my tensor, is just going to be your diagonal tensor, v inverse. I'll write v inverse because that's all that really matters. 1 over sigma 1 squared, 1 over sigma 2 squared, dot, 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 down to 1 over sigma d squared, and zeros everywhere else. By the way, if you ever write up this problem in a piece of code, don't ever create that. Don't ever create an object that's mainly zeros. Write your code in a way that you don't ever instantiate the zeros. Doing linear algebra on tons of zeros is a really bad idea. For one, it's slow, and for two, if there's any issues with your linear algebra system, it'll start to throw in numerical issues. So don't ever do that. But conceptually, yeah.
Not only D components in our Y, we've got D data points.
Good. The question is, what's this D, and why do we have D data points? So I'm assuming that there's 13 data points. I'm right about that, right? Yeah, that's 13, including that one. So this data set, in some sense, is 13-dimensional. It's got 13 points, and I'm going to assemble them into a 13 vector.
Okay, so D is just taking the place of the vector.
Yes, I could have called it capital N. I'm calling it capital D because I'm thinking of it as the dimensionality of my space. This is just the nth point of the D. I should have called that point I, for physicists. I mean, different communities, by the way, subscript with different values. And by the way, for some communities, if you call your data anything other than Y, they get confused. Like for some communities, so I always call my data Y in all the papers I write, because some subset of authors, or of readers, get confused if the data aren't Y. Anyway. It's called Y and Y star and Y tilde. Okay, good. Now, yes, go ahead. Question from the audience, is the V matrix always this cute diagonal thing that's mainly zeros? The answer is no. Why are all of these terms zero? All of these terms are zero because we've assumed that the data are independent, meaning there's no covariance between any 2 points. Points just have variances, but no covariances, which is true for a lot of experiments. That is true for a lot of data, but it's not true for all data, and it's not true in general. Yes? I won't go as far as to say invertible. The question is, are all covariance matrices invertible? The answer is that all covariance matrices have to be non-negative semi-definite, which means they can have zero eigenvalues, but they cannot have negative eigenvalues. They have to be symmetric or Hermitian, because they have to have real eigenvalues. You can't have imaginary variances. Notice that if this thing had if V had zeros in it, that would be equivalent to a data point having no uncertainty. And V inverse would have an infinity in it. And that data point would be more valuable than all the data that have ever been taken in the history of mankind. So really, they do have to be invertible. You see why? Because as a data point gets big, the variance goes to infinity, but that's cool. You can invert an infinity. You just can't invert a 0. But you never get a 0. See how beautiful it is? Like, information theory protects you. And by the way, the inverse variance is often called the information tensor, because the eigenvalues of this are, and the eigenvectors are the directions on which you have information, and the eigenvalues tell you how much information you have on those directions. Inverse variance is information. Yes?
I seem to remember that taking the determinant of a diagonal matrix is fairly trivial.
It really is. It really, really is.
Why were you saying it's a really difficult?
The question is, taking the determinant of this matrix is not hard. Therefore, why were you saying stuff about taking determinants is hard? It's because as soon as this becomes at all interesting, it becomes hard. And also, we're going to, even in our inference, we're going to find a determinant that is at least a little problematic in the inference we're about to do. Questions? Okay, good. Good, let's do statistics or something. Okay, now, so the total probability for my data, okay, so now it's time to get serious. Okay, good. So the total probability, the probability you might write down for all of my data, like all the data, which is, if you use this kind of notation, the set of allyn's going from 1 to d, the probability of all the data given theta and various other things. By the way, one of the things Bayesians like to say is there's no unconditional probabilities. Probability of these data is conditioned on our parameters. Also, all that housekeeping data, all the x's and sigmas. And also, all of our assumptions. Right? The probability we write down is conditioned. This thing means conditioned on. Probability is conditioned on. It's conditioned on a hell of a lot of stuff. Like a list of our beliefs. So I sometimes just put that in as a symbol. The list of everything we believe. Or actually, it's not even the things we believe. It's the things we claim to believe for the purposes of doing this data analysis. This is just the product over all thoseyn's given theta, xn, sigma n, or whatever I called it. But I could just as easily have said that this is the thing I wrote down there, n of y given mu phi, where y is this, mu is that, v is that. And do you see how this is the same as this? Anyway, if it is not obvious, that is an exercise to the reader that this equals this with those definitions. Okay, good.
Don't we need to know what f, x1, and x2 are to demonstrate that those things are equivalent? We need to know those to demonstrate that the...
No, because I've said that in mu, the elements of mu are f evaluated at the things. And in my definition for this p of yn, I said the mean is f of xn. So this statement is trivial in the mathematical sense. It's not. There's no content to the statement that equals that. It's just a translation. The reason I like this translation, though, is we get this beautiful quadratic form in it. And so if I asked for the log of this probability, the log, again, large parts of the world do not use this symbol, which all physicists use. Of p of yn given blah, 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 is stuff minus 1/2 y minus mu transpose v inverse y minus mu. Where stuff stuff includes the log of a determinant. Now I have a million things to say, but I do not have a million minutes. But one of the things that I would say here is that, do you know how, if you in like Python ask for the determinant of a matrix, do you know how it computes it? It does some kind of eigenvalue. It does some kind of factorization of the matrix, takes the logs of the eigenvalues, adds the logs, and then exps it. So you should never take a determinant. You should take the log. And you'll notice for every determinant function, there's a log det. There's det and there's log det. You should never execute det. In fact, if you ever look into the source code, det is a call exp of log det. So don't ever take a det. Always take a log det. That's all you want anyway. We always will work in the logs. From now on, that's the last time I write a pure probability. Everything will be log probability. We will always work with log probabilities. Now, why did I write stuff here and not log det? I should have written log det of 2 pi v here, or negative log det of 2 pi v. I should have written that there, but v contains only housekeeping data. V does not contain our data or our parameters. See, it only contains this metadata that's known, so we don't really care about it for now. Later we're going to care about it, but right now we don't care about it, so let's just call it stuff and forget about it. And then we have this beautiful quadratic form. Quadratic forms. Yes?
Is there any reason other than wanting the quadratic form to take the log of probability? I'm not sure if there's some sort of conceptual reason.
There are many. The question is there any reason other than the beauty of the quadratic form to take the log? Yes, there's 2 other reasons that I will say enigmatically and not explain in any detail, but one of them is all friendly probability distributions are in the exponential family. So Poissons and Dirichlet's and all these, there's all these different friendly probability distributions. They're all betas, they're all exponential family. So usually taking the log leaves you with something fairly tractable. Sometimes it involves some beta functions and stuff that are horrible, but whatever. And then the other comment is, when you're writing code, you want to work in the logs because you generally have immense dynamic range. So if you look at the data as I've drawn them, if I'm evaluating this function here, you see how this function is going to be e to the minus, 4, and this one's going to be fine. So there's quite a bit of dynamic range between this data point and this data point if we were just multiplying together probabilities. There's much less dynamic range if we're in the logs, and so in general, you put less stress on your code if you stay in the logs. That's really the reason I work in log. I'm very much thinking about numerical stability. Yes? The question is about free energy. Very nice. There is a whole formulation, a whole Hamiltonian formulation of data analysis. So in addition to the geometric formulation of data analysis, and I'm very much a geometer, there's a dynamical formulation of data analysis in which this thing represents some kind of exponential of a potential or a potential energy. This is like an energy function. And the exponential of the energy function, when do you ever exponentiate an energy? It's when you're thinking about Boltzmann factors like statistical mechanics. How much time does a molecule hang out at different energies? And then finding like the maximum likelihood solution is going to be like going down to the minimum energy state. See, there's going to be something like that. And then in MCMC methods, there's a whole Hamiltonian family of MCMC methods that literally treat your data analysis as a stochastic dynamical process. And you run the stochastic dynamical process, and your code fairly samples the probability distribution because molecules fairly sample the energy landscape. That is like awesome. And that's all I'm going to say about it. I'm done. But it's worth looking at. And a lot of the computer science community, in the computer science community, people often talk about these problems in terms of energy. In fact, you'll even see in computer science things, they'll like attach parameters to data with springs. And they'll say, we're trying to get the parameters as close to the data. Like they'll draw the function as being attached to the data with springs, and the spring constants will be related to the inverse error bars squared. See? See how if I did that, I would get a quadratic energy dependence on the function that would look exactly like this with this. See? Cool, eh? Anyway, there's literally diagrams in computer science papers with like springs on data points, because people really do think that way in computer science. Oddly, the physicists never draw that diagram. Thoughts? Okay, I can't help myself. There's one other comment I want to make, which is that when I, and this is like way off topic, but if somebody wanted to put it onto the brainstorming document, they could. When we communicate about models like this, and we try to communicate across domains, there is a common language for communicating across domains about problems like this, and it's called graphical models, or sometimes directed acyclic graphs, or sometimes probabilistic graphical models, whatever. And this problem can be drawn, the assumptions, and it's a way of stating your assumptions. I can state a large fraction of those assumptions with the following diagram. This diagram does not state all of the assumptions, but it states a lot of them. I have observed data yn. That each data point is generated by a set of model parameters and its x value and its uncertainty value. And I have d points n. That model, that diagram there, you can show that diagram to a statistician and they'll be like, oh, okay. And what does it tell them? It tells them a bunch of the assumptions. It tells them that theta is shared by all data points, but it says that all the data points are independently drawn, and that each data point has its own housekeeping data, xn and theta n. Actually, I should even write it like this. There's an even better way to write it like this, theta n. If I write these as dots, xn, then it even indicates to them that these are considered to be known and not inferred. Parameters we're not trying to infer. If I draw them as dots, this double circle says that this is the data, and this is the thing we're trying to infer. So there's a whole language of these models, and they have a very specific set of rules, and if you follow the rules, you can communicate with a wide range of people. It's a very interesting thing, yeah.
Does that also encode the fact that there aren't covariances?
Yes, the fact that we're in the box says that there aren't covariances. The box says you're repeating the data points identically. And the fact that we've included the error flag inside here means that we're allowing them to have different noise properties individually, but they're each independently drawn. Anyway, there's a whole language like that. It's great, very useful. Not going to talk about it. Okay, good. So, comments. This thing here is called the log likelihood. It is a function of theta, because theta is over here, but it is evaluated at the data. This is a really weird thing. This thing looks like it's a function of the data, but the whole point is you don't get to change the data. You got the data. They're your data. So the likelihood function is really a function of these parameters. See how weird that is? And by just making those statements, you can see that I'm a Bayesian. But there are But the likelihood function is the fundamental entity in both frequentist and Bayesian inference. In Bayesian inference, the key thing is the likelihood is the only source of information. So meaning you have some beliefs before you start this experiment, you have some beliefs after you finish the experiment, and your beliefs were updated entirely with the likelihood function and nothing else. So the Bayesian position, the Bayesian kind of principle is that, it is called the likelihood principle, is that this is completely sufficient object for transmitting information. If you're transmitting the likelihood function, you're transmitting all of the information. There is no other information beyond the likelihood function to transmit. So that's the Bayesian, why it's so important in Bayesianism. The reason it's so important in frequentism is that Kramer-Rao bound saturating estimators, meaning the best estimators you can possibly make, are optima of likelihood functions. So if you can write down a likelihood function, you can deliver also the best possible estimator for your parameters. And it's really best possible under some rules of what the Kramer-Rao bound is, which I'm not going to state, because I'd have to have looked at a Wikipedia page before starting. But it has to do with asymptotically unbiased estimators. So the likelihood function is an extremely important object, no matter what your statistical philosophy. And to cartoon it, if I was going to give you the cartoon level is this. Cartoon. A frequentist optimizes, and a Bayesian now what do I write here? I can either write samples or I could write updates probabilities. Both are happy when they see this function, because once they see this function, they know they can operate. The Bayesian knows they can update their beliefs, and the frequentist knows they can get a bound saturating estimator. So everybody's happy. Let's go frequentist, shall we? So the frequentist thing to do is to optimize this. And if we optimize this, if we optimize this, we will have the best estimate of these parameters we can have. So that's good. Now, notice here that it is very valuable that theta only affects mu. Mu is the only thing that's a function of theta in here. If theta also came into the noise model, theta would come into these v's, and then I would have a much more complicated derivative. You see I'm about to take a derivative of this? See how we're about to take a derivative? We're going to take a derivative of this. Take a derivative of this. If theta came into the v's, we'd have to take a derivative through the determinant, which I know how to do. I have a little cheat sheet of all my calculus on linear algebra operators things going on. In fact, I'll post that to the wiki, by the way. I have a great cheat sheet, which I'll post to the wiki. Don't let me forget that. With such things, but oh my God, it's unpleasant. Okay, good. It is now time for us to capitalize on assumption 7, because then we can make taking this derivative extremely easy. You ready? So what does 7 mean? Assumption 7 means that f of x, I should have done that as a, f of x semicolon theta is some kind of sum of, it looks like this, it must look like this, over k, theta k times f, call it g sub k of x. Okay, now, what does that mean? Well, that means that I can write this mean vector in a very, very simple linear algebra way, okay, which is, it's going to be some matrix M times this little vector, which will just be theta 1, theta 2, to theta k. So if I have k, or capital K, I guess this needs to be, k equals 1 to capital K, I just have a little set of parameters which I can multiply by a set of function evaluations, and that will be this operator will give us mu, this vector mu. We can write mu as just a product of some matrix times a set of parameters. To get very specific, let's imagine we had a quadratic model. Let's imagine we wanted to fit these data with a purely quadratic model. Example. Quadratic. Well, what's the quadratic model? The quadratic model is that f of x is, I want to write it in a nice way, whatever, a plus bx plus cx squared. Right? Good. In that case, the matrix M, sorry, I'm going to make myself a little space. This is why boards should not be. Okay, good. M becomes 1, 1, 1, 1, 1, and x1, x2, to x sub d. X1 squared, x2 squared, to xd squared. And theta, a, b, c. See, now when I do the multiply, look, a plus bx1 plus cx1 squared, that's our prediction for y1. And then a plus bx2 plus cx2 squared, that's our prediction for x2, and so on, you see? Good. So now, mu is just m dot theta, and now we can take this whole derivative. You ready? Look at this thing. This now becomes an m dot theta. You see this thing right here is becoming m dot theta. And this thing little here becomes m dot theta. And notice M is a rectangular matrix. M is not a tensor. So you should start to get concerned. It's not a tensor. It's not. But of course, everything important is a tensor, so tensors will appear. But notice now, this is a quadratic. This is a pure quadratic. This is a symmetric matrix. I've got the same thing on each side of it. So I could flop it the other way. Or you can think of it as this squared divided by this. See? And when you take the derivative of something squared, you get a 2 out front, which kills your half. See? Minus sign. There's some interior minus signs. Can you see it? Can you see the derivative now? The derivative is something like, I'm working without notes here. The derivative is, so I'm going to take the derivative of the ln likelihood with respect to theta, because now, of course, I'm being very loose with my terminology here because theta is a vector. Remember, ln likelihood is a scalar. This object's a scalar. It's stuff, which is a determinant, plus this is an inner product, right? This is a set of dot products in a non-trivial metric. So this is an inner product, it's a scalar. This stuff is a scalar that doesn't depend on theta. So the derivative with respect to that is 0. That's why I called it stuff. d stuff d theta is 0, so it's out. So we only have to worry about that. The 2 is going to come out front, and it's going to just be, God, I hope I get this right. It's got to be V inverse acting on the stuff in this thing, oops, y minus m dot theta. It's like the residual times this with an m transpose out front. Is m transpose right? Yeah, it's got to be m transpose. And maybe there's plus or minus, but we don't really care because we're about to set it to 0.
How does this define what kind of optic do you get out of that? Are you supposed to get scalar?
Good. Boy, that's barely visible from the front. This is a scalar. We're taking the derivative with respect to a vector. This is in the quadratic case, this is a 3 vector. So this thing better be a 3 vector that we get here. Now, is it? Well, let's check. This is d by d. This is d, this is d. D by d acting on a d vector leaves me a d vector. This is 3 by d. This was d by 3. This is 3 by d. D by 3. This is 3 by d. 3 by d acting on a d vector gives me a 3 vector. So this is correct. This is 3 by d. This is d by d. This is d. So it checks out. That was a very good question. That question for the audience at home is, what dimension is this thing? It's a 3-dimensional vector in this case, and it does work out. Did I take my derivative right, by the way? Is there a minus sign? There shouldn't be, but sometimes there is. I don't really care because we're about to set it to 0, so who cares? Maybe there is. I mean, there's a bunch of minus signs to worry about, but who cares? You just have to think about which way it goes, and anyway, doesn't matter. Okay, good. Now, if you're a frequentist, you're setting this to 0 because we're finding the optimum. And the nice thing is, because this problem is so beautiful, it's a pure quadratic form, and we have a linear operator inside the quadratic form, this thing is convex. For the same reason that a parabola is convex, right? Once you have a parabola, you know you have a parabola, you can just go to the bottom of the parabola. Wherever you are, you just go downhill and you will get to the bottom of the parabola. It doesn't matter. So that's what I mean by convex. Convex has an actual mathematical meaning, which I won't state. But what it means from the purposes of data analysis is if you just go downhill from wherever you are, you get to the right answer. So this is convex. So that means if we can find this derivative to be 0 anywhere, we've got the optimum 0, the only 0 in the whole problem. Well, if we set this to 0, it looks like if I set this to 0, I get, so this thing is 0 at some estimate of the parameters. I'm going to put a little hat on theta to say if I set these parameters to their theta hat values, I get 0. Those theta hat values are going to be our frequentist estimator. And I'm setting this to 0, so what I'm going to do is I'm going to take this in here, and then I'm going to move this to the other side. Got me? This is going to lead to the equation m transpose v inverse y equals m transpose v inverse m theta. Unhappy. Oh no, totally happy. Now, what's this look like? What's this thing? This is a 3 by 3, see? See how that's a 3 by 3? Because which is pretty cool. 3 by 3 acting on the 3 vector. That gives me a 3 vector. What's this thing? Well, this is a d vector. That's d by d, so that's a d vector. That's a 3 by d, so this is also a 3. So both sides are 3 vectors. So we're good. That's cool. So now let's get theta hat. What do I have to do? Well, this problem, we can pre-multiply both sides. We can left multiply both sides by the inverse of that thing.
Is it going to be invertible?
Good question. Is it going to be invertible? Oh, good. Let me write the answer. Let me write the answer and then ask whether it's invertible. Great question. Will it be invertible? And this is an equation every person in data analysis has written so many times, it's like a song that sings in their heart. M transpose V inverse M inverse M transpose V inverse Y. That is the solution of the least squares problem, where every point has its own uncertainty. And notice, nothing about this solution actually assumed they were independent. This also would have worked with dependent data as long as we knew all the covariances. Now, the question arises, is this invertible? The question of whether this is invertible is the question of the eigenvalues of this object. And that has to do with whether or not the columns of this matrix are linearly independent with respect to this metric tensor. Remember what linear independence is? Linear independence is there's no non-trivial way to make zero sums out of the three vectors. Now, in a non-trivial metric space, it is still that, but you want to work in that metric space. Anyway, it's a little, you have to think about it a little bit. It's a slight generalization of pure independence. Because these three vectors could be independent, but only along a direction on which you have no information. You see? So it's a little bit more complex than the linear independence you learned on your parents' knees.
How do you make x1 independent of x1 squared?
The point is that this vector, when evaluated at the x's, is linearly independent to these two vectors when evaluated at the x's. Does that help?
No.
It is that. So, nearly there. You can think of this column. Think of this first column as a very strange D vector. It's a vector that has ones in every coordinate. This is a vector that has some numbers in every coordinate. This is a vector that has a different set of numbers in every coordinate. So this vector and this vector are not parallel in any sense.
But each component of the third vector is the square of the same component of the second.
And yet there's no sum of these two vectors you could make that would create that vector. Which is the question about linear independence. And then you just have to add this thing where you weight it by the eigenvalues or eigenvectors or whatever. You project onto the eigenvectors and weight by the eigenvalues of the information tensor. There's some other details. Good. Your question though is very good. It's not the case. It's not the like in a. This is the word independent is so overloaded. It makes linear seem sensibly defined. Independent has so many different meanings. The independent that's used here is completely different from the independence that is relevant to the invertibility of this matrix. They have no relationship of any kind, those two independences. And there's all sorts of other, people talk about independent variables, dependent and independent variables. So in the stats literature, X is sometimes called the independent variable. Anyway, good. The reality is that in general, the time when this becomes not invertible is times when the model becomes very complex. I have 13 data points. Imagine I'd use 2,000 functions in here. If I use 2,000 functions in here in a 13-dimensional space, 2,000 vectors can't be linearly independent. At most, 13 of them can be. And so then you definitely will get this not being invertible, and then you have to do new things. Of course, we know how to do those things, but it's a little beyond our current scope. Yes? No priors have been incorporated because we are being a frequentist right now. This is a frequentist estimator. By the way, this estimator has tons of absolutely gorgeous properties. Oh, I'm out of time. How did the time fly? Okay, so I'm out of time. Let me just make a few very short comments, and I will release everybody. We can start the beginning of the next one with a little discussion of this. First of all, look at this operator here. You see what this operator does? This takes our d vector of points and collapses it to a 3 vector. And then the only thing this gets to see is this 3 vector. So this thing produces the 3 sufficient statistics that were originally in the data. It finds the 3 sufficient statistics you need to do your inference. And then what is this? This is like a shear operator. It does an affine transformation from the 3 sufficient statistics. It shears them into your parameter space. So this dimensionality reduces the data to a subspace that is sufficient, and this transforms the subspace into your parameters. See how beautiful that is? That is geometry orama. Yes?
So here is like a huge compression of data, or
yes.
So when does this break down? When you don't make the option?
Good. There's so many. I mean, we are out of time to ask exactly what goes wrong when we break these assumptions. But actually, that book I mentioned earlier, this Mackay book, Information Theory, Inference, and Learning Algorithms by Mackay, is about this point exactly, about the point that data analysis is data compression. That is, once you make these assumptions, you're saying, I can compress the data because I have a model for the data. So data analysis is compression. The fact that this is a compression of the data actually doesn't fall down to any of these assumptions in particular. The fact that it has this beautiful structure where it's really a linear dimensionality reduction followed by a linear affine transformation, that comes from the fact that the model is linear, that the noise is Gaussian, it's known, and so on. There's a lot of things that cause that, and breaking any of those will break that simplicity. But no matter what assumptions you wrote down, your inference would be a dimensionality reduction. In general, you're always reducing the size. And there's a whole theory of this called there's sort of a message length way of thinking about data analysis. That instead of transmitting the data, you transmit model parameters plus residuals. And that's smaller than your data, it turns out. Anyway, I literally have blown the time. So we don't have time to say yet what happens when we break these. So I will say a little bit about that before we get into MCMC next time. And that will also let me talk about priors. So we'll bring in priors when we bring in MCMC and move to Bayesianism. Okay, good. See you tomorrow.